making a mess here.
Yeah, I don't like to change things if they don't need to be changed either.
All right, so let me introduce you
Okay.
to our class. Professor Surjit Sen. I think if his first qualification, he is a good friend of mine. Yes, and he's a professor in State University of New York in Buffalo. There are two universities with the same name. One is a college and another one is the university. So he is in the university. He is a Fulbright fellow and he is also a Jefferson Science Fellow. Means he has worked for the US government in designing science policies related to Africa, which we have a person from there, and he's a physicist, and his interests are in non-equilibrium statistical physics, non-linear dynamics, and social systems and development studies. But that was his role when he helped the US government in framing their science policies. So with that, I'm going to stop, and he wants to share some things with you. You should feel comfortable in asking questions at any stage. And all you have to do is raise your hand and I can interrupt him. And also, you will be writing a one-page report like you have done in the past. And this is our last visitor. After that, it will be just me, who will be lecturing here. So with that, let me stop and invite Professor Surjit Sen to share his experiences.
Thank you, Alok. Can everyone hear me?
Yes, they can.
Okay. Yeah, just I'll be keeping an eye on you. So if there is a question, you alert me to it. First of all, unfortunately, I can't see anybody in the class other than Professor Kumar. So that's so I'm flying blind, which is never optimal, but that's okay. Thank you, Alok, for the nice introduction. I'm very much like him. I'm a physicist. I'm his friend. And I have been in Buffalo for close to now 30 years, which is long time, I think. So one of the things that I realized along the way is that I was as a physicist, I was trained to be a very serious guy, asking very, very big, big and precise questions, and working myself to tears, trying to define my questions and set up very accurate mathematical answers, making sure my answers were consistent with observed experiments and all kinds of stuff like that. So these are the things that I was trained to do. And dutifully, I did that for a long time. And ultimately, I came to a point that I realized that I was taking life, certainly life as a professor, more seriously than I needed to. So this was when I started having a bit more fun. And this particular talk is kind of an upshot of my musings. And I thought I would share it with you. I actually will not talk to you about much detailed physics at all, but really try and hopefully convey to you that I have learned to think the way I used to be able to think when I was a kid. Little questions, hence, and never satisfactory, incomplete big answers. That's what I'm going to tell you about. I know you always ask questions. You perhaps think that they may not be the big questions you need to ask, or the precise questions you need to ask, or the right questions you need to ask. I want to tell you that every question is great. You'll be surprised at the power of your questioning if you could find the answers. And by and large, we know answers to very little things, very little questions. Okay. So with that, I know this one is always going to object. There we go. So how about some general little questions? First little question is, almost all questions are driven by curiosity. So what is curiosity? Now you can come back and tell me, well, that's a question in psychology, or that's a question in biology, or perhaps brain science. And yeah, fine, but remove the walls. What is curiosity? Curiosity is all about our ability to ask questions. In fact, curiosity is intrinsic to our very survival as animals, let alone as humans. So it's not just that we are curious. Everybody's curious. And I mean, really, everybody's curious. Every living thing that I can think of is curious. So curiosity is something that you must never lose track of. And you want to cherish the fact that you're a curious person and be as curious as you can be. That's a good thing. Second thing I will tell you, and I'll get into the details of these things. Just ask a question, whatever question you have, because most simple questions turn out to be surprisingly important and surprisingly difficult to get answered. We think about what is important to do, what is useful to do, and so on and so forth. But do not underestimate the importance of useless knowledge. It's incredibly important. And I hope to tell you a little bit more about it. All of us ask the questions as to who we are, where we are, how did we get here, and what's going to happen to us. These are all tied to our relationship with the universe. I'll touch upon that briefly. And I think that's always something that most humans that I have interacted with have gone through. I'll talk about the pale blue dot. The pale blue dot is to describe planet Earth from space. And this particular phrase was coined by Carl Sagan, the very famous astronomer from Cornell, who made enormous contributions in making astronomy accessible to everyone. And finally, I would like to leave you with thoughts on learning and thinking holistically. Don't think that you are, so-and-so. You are not so-and-so, you're you. And what you think of a problem, what you see as a problem should not have to be confined by the walls and barriers that are built by the academics of the world. In fact, that's detrimental to learning, that's detrimental to pursuing and understanding the complexity of learning. So what is curiosity? Because that's where I began, right? The psychology and neuroscience of curiosity is an open subject. We don't understand curiosity very well. We certainly don't understand its biological underpinnings, nor do we understand its more detailed psychological underpinnings. What we know is that curiosity is something that is very intrinsic to us. It certainly has biological signatures. It certainly has signatures in our mind as measured indirectly through various biologically relevant parameters. Psychologists also measure it, obviously, because they measure the activities of the brain and so on. But at any rate, I want to tell you that curiosity is very important. and curiosity is good for you. Here is a news story about the work of Emily Campbell. Emily Campbell did her PhD at UC Berkeley, University of California at Berkeley. And this was about 6 years ago. And there was a news story that was written about Campbell's work. And this is the excerpt from the heading, 6 Surprising Benefits of Curiosity. For children and adults alike, curiosity has been linked with psychological, emotional, social, and even health benefits. It's good for you. See, I told you that. Curiosity and pathways to well-being and meaning in life. Wait one sec. Traits, states, and everyday behavior. This is an important paper. It's a much more serious paper by Cashton and Steger. I won't get into that. But what I'm trying to tell you is that curiosity is very good for you, and you can certainly educate yourself a lot more about curiosity as you go along. See, I'm not talking physics, but you've got to be curious to do any science. I also told you about useless knowledge, pursuing useless knowledge. So I'm not the first one to tell you this. This gentleman here, his name was Abraham Flexner. Abraham Flexner lived in the later part of the 19th century, and he passed away in 1959 at the ripe old age of 87 or so. The current medical education, if you're going to go to med school, what you're going to go through has the footprints of Abraham Flexner's work. Current medical education was designed by Flexner in the 1920s. Okay, this man did it. So whatever you know or you don't know, you like or you dislike, Flexner did it. He was a major reformer of medical education in the US, the founder of this very famous institute that you may or may not have heard of, the Institute for Advanced Study, which is part of Princeton University. So is it not a curious fact, Flexner wrote, that in a world steeped in irrational hatreds, which threaten civilization itself, and you know that, right? You listen to the news. Men and women, old and young, detach themselves wholly or partly from the angry current of daily life to devote themselves to the cultivation of beauty, to the extension of knowledge, to the cure of disease, to the amelioration of suffering, just as though fanatics were not simultaneously engaged in spreading pain, ugliness, and suffering. This kind of knowledge for the sake of pursuing some curiosity was recognized and extolled by Flexner in 1939 in an essay called Usefulness of Useless Knowledge in a very strong way. And that had a profound effect on education and research in the United States and the rest of the world in the early part of the 20th century. And while you agree with it or don't agree with it, it is difficult to get away from the fact that Flexner had a message to convey, and the message has its merits, whether you like it or not. Let me make sure I want to be exactly on this slide, yes. So where are we now as human beings? If you look at these two dots here, the white dots, or more like rectangular shaped objects that you see here, this is Voyager 1, which is a spacecraft, and this is Voyager 2, which is another spacecraft, both launched from planet Earth. Both of them were launched in 1977. So 23 plus 21, 44 years ago. And so 44 years, some months, they were launched not very far apart in time. And they were essentially launched to space. They were just sent off to space. They were given some nuclear power to power themselves up to a certain point in time. After that, they would become useless. The amount of power they could typically probably have in those days with the technology we have would be of the order of 50 years or less, more like 40 years. We are currently at a time when these spacecrafts are sort of semi-dead. We still get some signals from them. the signals are very, very weak. But when we can read those signals, we get data and information that is of unbelievable dimensions for us. So Voyager 1 and Voyager 2 were launched in two different directions of the sky. So if you look at this darker blue region, this is the region around the sun. Okay, so the entire solar system that you know of is contained in this darker blue region or brighter blue region, with this termination shock around as the boundary. So this is where all the planets are, all the asteroids are, the area around the planets, which is called the Kuiper belt. I don't know if you've heard about it. I'll come to that. That's also in here. And this is the region, the broader region is the region, the blue region is the region where the effects of the sun are felt. The effects of the sun are very important. You and I don't know this very much, right? We only feel sunlight. That's because of the atmosphere. But if you take away the atmosphere, the effects of the sun are so strong that they will obliterate us in basically not much time, seconds, perhaps. So sun is a very dangerous guy. Sun is continuously emitting charged particles around because it's a star, it's burning up, it's fuel, right? So this is the fuel burn up that you're seeing, this blue region. But when you get away from it, you get into what one would call the space between the stars, because the sun is a star. So if you get away from the effects of the sun, you get into interstellar space. The Voyager 1 and Voyager 2 are actually now in interstellar space. So what is special about interstellar space? Well, the solar particles go down, but non-solar particles come around. What we are seeing in that non-solar particle content from the very, very weak signals we see now is that we are seeing primordial organic molecules, the building blocks of life in that interstellar space. So those signatures are now coming out. So just to get a perspective again of where we are, this is how the Voyagers look like on the left side. They don't look very impressive, according to, when you compare them to Elon Musk's spaceships and so on. They look pretty boring, in fact. But these guys are really our whiskers far, far away, right? Places that we'll never be able to get to. This is a cartoon that shows the sun and the planets, and then this dense white area, which is mostly made of rocky material, which is called the Kuiper belt. So the Voyager is far away from these regions now, far out of it. But there is this enormous region which still has solar particles, not much solar radiation, but solar particles, comets that have gotten sucked into the ambit of the sun and so on and so forth. This region is called the Oort cloud, OORT, Oort cloud. Oort cloud is a vast cloud. Okay? So I'm not going to tell you much about the Oort cloud. But what I want to tell you is that we are very much in the Oort cloud. Okay? So we won't be able to get out of Oort cloud. By we, I mean Voyagers, won't be able to get out of the Oort cloud in the next 10,000 years. So relax, enjoy the Oort cloud. We are there, but that's good enough. That's telling us a lot of stuff. So quite a long time ago, I think this picture was taken around 1990. Yeah, February 1990, it says in tiny font. Voyager 1 was around here. So this is the solar system. This is where Voyager 1 was. And Voyager 1 took a mugshot of planet Earth. This is the mugshot of planet Earth. And this, of course, is planet Earth, shown inside the white circle. That is the pale blue dot that Carl Sagan named planet Earth to be. So everything that you know, I know, anybody else in the world has ever known, every person, every species, every plant, everything is there in that pale blue dot. That's how significant or insignificant we are. Not even in the scale of our galaxy, just in the scale which is sort of just beyond the regular solar system or at the outer edges of it. So we are nothing really. We are incredibly insignificant in the context of the universe. So what are we with respect to the universe? Where are we? I pose these questions, right? Amazingly, it turns out we can still figure out a few things. We can figure out that the universe actually formed about 14 billion years ago. Imagine that. We know this for a fact. We can prove it. Isn't that amazing? How can we be so sure? Given this vast universe, that little blue dot we are in, and we super tiny beings, impossibly small to see from that perspective, or even from the perspective of just being in outer space around Earth orbit, we can't be seen, right? So how could be so audacious as to be certain that the universe formed 14 billion years ago, an entity that we can't even measure? We'll never be able to measure. This is the power of the human brain. This is the power of curiosity. I keep coming back, right? So the way this thing worked out was very interesting. Back in 1960, just after Abraham Flexner passed away, two gentlemen were hard at work trying to figure out what are the heavy elements in the universe. We all know, or we have long known, that heavier elements form later in time. So first, the universe only had hydrogen because the universe had a lot of energy. And when there was too much energy, you couldn't form larger nuclei, which tend to be less stable. They kind of fly out. But hydrogen, which has only one proton, was therefore the primordial matter that formed when the universe cooled down enough to actually form, neutral atoms or ions. So after hydrogen came helium, which has two protons in the nucleus, and so on and so forth. So we know that as the universe cooled, as time passed, the heavier and heavier elements formed. So by looking at the amount of heavier elements present, one can estimate how old the universe must be. And this is exactly what was done. Hang on one sec, sorry about that. One sec, sorry about that. I thought I had turned my phone off. There we go. It won't bug me again. So these two gentlemen basically figured out from that estimate what the age must be. The guy on the left is a fellow called Willie Fowler. Willie Fowler was a boy from Columbus, Ohio. He became a professor. He actually went to graduate school at California Institute of Technology when he was like 22 years old, and he never left Caltech. So after graduate school, he eventually became a professor there, and he spent the rest of his life passing away in his mid-80s at Caltech. And I had the good fortune of not only meeting Willie Fowler, but talking to him and listening to him. And this guy was a riot. If he doesn't look like a riot, that's too bad, but he was a riot. The guy on the right is a fellow called Fred Hoyle, Sir Fred Hoyle, the Brit. These two people, they did a lot of work together, along with some others whose names are not mentioned in this particular work. But this paper is very important because it captures those two names and led up to their Nobel Prize later on. Fowler got the Nobel Prize first, and Hoyle, the guy on the right, got it later for different work. But they were among the first people who estimated the age of the universe, and their initial estimates were not all that great. They said the universe is has a mean age of 11 billion years. And this 11 billion can vary between 5 billion and 17 billion. That's what they said. And it turns out that the age of the universe as we know it now is about 13.7 or so billion years. So it's somewhere very close to what their estimate was at the time. All right, moving on. I won't waste time. This is how the universe probably formed in some kind of a of an event. Tiny fraction of a second later, it looked like a hot soup. Then it became a colder soup. This is the baby picture of the universe. And then matter formed, and the galaxies formed, and we formed, and so on. So our planet, as is the case for much of solar system, emerged about 4.5 billion years ago. So we are roughly a third of the age of the universe. That's about how old we are. So you pick up some dirt from the ground, that's about how old that is. About 4.5 billion years. That formed state, that is. Of course, matter formed way back when the universe formed. Slowly after that, shortly after that. So moving on, I also want to tell you something that you may not have been thinking about. There are beautiful leaves out there in your neck of the woods. Certainly here in Buffalo, we have nice colors. Fall is around, soon winter's coming. My snowblower has to be started up. All these seasons and colors that we get is because our planet, if you will, is peculiar. How? Well, you know that we go around the sun. That's not a surprise. What is peculiar is we are tilted. Our axis, if you will, is tilted with respect to the solar axis or with respect to some kind of what we can call vertical at a certain angle. This angle happens to be 23 some degrees. And it is extremely important for our survival because it is this tilt that gives us seasonality. And if this tilt were affected, we would be severely affected. We are very fragile creatures. The slightest wobbling will affect us quite a bit, and it does. Earth does wobble. So all these things are tied to the fact, the fundamental question, who we are and what we are doing here, right? I wanted to bring that in. Now let's look at Earth itself, our planet, our home base. You hear about global warming, you hear about sea level rise, you hear about fires. What's going on? You hear about Greta Thunberg and what have you. What's going on? What's really happening? The short answer is yes, we are warming up. Yes, there is more carbon in the air, but we don't know a heck of a lot. So I'm going to tell you a little bit about what we know as of 2021. So if you look at the figures, there are three figures I have put up for you. The figure on the extreme left, this particular figure shows the concentration of oxygen 18. Oxygen has the number of 16 nucleons, but 18 is a heavier oxygen. So by looking at oxygen 18, you can tell the following: if the parts per trillion, I think, is high, then that means the Earth is cooler. And if the parts per trillion come down, that means the Earth is warming up. So as you can see, stars were wiped off about 60 million years ago. And this is the time when the Earth was beginning to cool down. And the Earth became much cooler. And ultimately, about 3 million years ago, the first humans emerged in Africa, the African hominids. And the African hominids existed on this planet for a long time, occasionally getting completely wiped off by a super volcano or another. And ultimately, our species came around, the Homo sapiens or Homo sapiens sapiens, to be more specific. And soon after we came around, you can see that this oxygen concentration became quite unstable. Part of this fluctuation that you see are normal climatic fluctuations. And these normal climatic fluctuations have been going a little bit off kilter for whatever reason we don't know for quite a while. Certainly African hominids were up to no great technology at the time. So here we arrive 500,000 years ago. We were actually technologically not very savvy either, but things were still going a little wild, even as we arrived. Planet Earth itself was doing certain things in its evolutionary track. Turns out that if you now look at the carbon dioxide parts per million, ppm here, what has happened in the last 400,000 years or so, last 500,000 years odd, is that these fluctuations have gone awry. You can see that in the last 100, 200 years, the carbon dioxide concentration has taken off. See this? It's off scale now. So clearly we have screwed things up really bad. There's no question about it. But what was the Earth doing before we screwed it up really badly? We don't really understand either. So our situation right now is not super good. Now, you are probably wondering, well, we know that carbon is a big problem. We know that the North Pole has melted away pretty much. The South Pole is melting away. Sea levels are rising. Floods are increasing. Yeah, absolutely. There's no disagreement there. No disagreement that climate was changing and we made it worse. But there are a few points to remember. If you were to look at those fluctuations that I showed you, right now we are actually up for a cold period. We were headed towards an ice age, mini ice age. That ice age got messed up by whatever has happened. That's one thing that's happened. Second of all, there appears to be a lack of understanding or knowledge about our climate. You see, our climate is no trivial matter. Our climate has the atmosphere, which is mostly what we call air. An atmosphere is very fluid, moves very quickly, light particles, not high density. It's an ocean of air. Ocean which is not very thick. It's a thin ocean of air on Earth. Now, our oceans filled with water, they are much denser. Sunlight only penetrates a part of it. The currents are mostly surface currents. But because it is so much denser and strongly perturbed by gravity, the dynamics of the ocean and the dynamics of the atmosphere, how they are coupled, we don't understand. Furthermore, the Earth is not static. The Earth is turning and tilted. So combined with that, what we experience every day as our weather or over time as climatic shifts, therefore is very complex. And the long and short of it is we don't get it. Even the best of computers don't get it because we can't simulate something that complex. It's simple. Part of my work on nonlinear stuff touches upon some of these issues indirectly. But I want to tell you something which is even more alarming. You see, most of the warming on Earth might be coming from water vapor, which makes clouds, and or carbon dioxide. We don't know how important which one is. So if you start looking at current literature, mostly based on experiments, you will find that the understanding is very incomplete. This particular paper I'm showing you from 2010 by Catherine Hansen of NASA, NASA's news team, who has written this. She has put it together, two sets of experiments, one by this Andrew Laces from NASA Goddard. They are trying to say that carbon dioxide plays a very important role, whereas there are other groups that say, well, water vapor may actually be playing even more important a role, which is what has led to this graphic here. On the left side here is water vapor, on the right side, the red one is carbon dioxide. They interact And it's the interaction of the two that causes this greenhouse effects, which we are so worried about. Anyway, this is something that I wanted to bring to your attention. Enormous need to understand these dynamical processes, and this work is very much underway, although we are running out of time. What's behind cloud formation? Even that is a question that needs to be understood much better. To make matters worse, COVID has screwed things up quite badly. You see, we are not really able to predict weather a few days ahead, even weather tomorrow, very accurately. Why not? Well, partly because I told you already that the atmosphere and the ocean are coupled, land plays a role, we don't really get all of it. So how do we predict? Well, the way we predict is every time an airplane takes off around the world, it collects data. It collects atmospheric data. That atmospheric data is used to compute what might be happening next day based upon what we know today. So because of COVID, when flights were cut down, our data quality went down. And as a result, our weather predictive abilities went down, which is why, I don't know if you noticed, but a lot of us noticed that the weather predictions really went for a toss for the last couple of years, ever since COVID began. So there are all these existential things. So here I have tried to give you the basic equation that, you know, some parameter at step I plus 1 is dependent upon the parameter at step I multiplied by this A matrix. So this is a column of numbers, and matrix, A matrix, that's the equation. It's the A matrix, that's what we are actually calculating or compiling from the aircraft data in this case. So I don't want to take up all your time. I just want to point out that almost everything I've told you today is transdisciplinary. Nothing at all can be tied to one discipline. So as you go through your undergrad years and grad years, or whatever it is you choose to do, I hope you don't lose sight of how important your own curiosity is, of your enormously developed abilities to ask questions and to seek answers. And often you will find that the questions you are asking are at the edge of knowledge, which is a good thing. In the university, we like to have walls. In the schools, we like to have walls because that was the system initiated in medieval Europe. Everybody has a cubicle. Physics has a cubicle, chemistry has a cubicle, history has a cubicle. That's not how it should be. Equitable society where everyone benefits, everyone wins, everybody lives in peace is really completely dependent upon our ability to treat each other for who we are and learn from each other and solve our problems. Because in this pale blue dot, that's all we have, and we are pretty insignificant in the scale of the universe. So I'll leave you with this thought. Here are just a bunch of problems that I think about all the time. I think about waste, I think about plastics recycling. By the way, there is no plastics pollution. All plastics are recyclable by definition. We are the ones in managing that. We don't do our job in taking care of the plastic waste. That's why we have made a mess of the planet. But you know, I've just laid around a bunch of problems for you here, and I wanted to, in the very end, just point out a little bit about dust, something that we don't even worry about because it's so simple and trivial. On the top left, you have a picture of northern India. Professor Kumar is from one of these areas, Kanpur, around here, in this area. And here you see the amount of dust, industrial pollution, part of it is also the pollution from agricultural fields that's been captured from space. Don't underestimate the influence of these kind of dust. 770 million tons of dust moves from the Sahara to the Americas every year. And you can see it from space, as you can see here. It's just wind blowing dust across the continents. We live in one fun place, I tell you. This is the Athabasca Glacier in I believe it's in Alberta. I've been there. It's in the border of Alberta and British Columbia, and so on. So anyway, I'll stop here. Everything you look at is fascinating, including dust. I love this quote from Sharon Begley, who was a science writer who passed away earlier this year. Somewhere something incredible is waiting to be known. So just go and ask the question. Thank you.
Thank you so much. By the way, I must say that the moment you started talking about curiosity, I started thinking about my own life and whatever I have achieved in my life. The bottom was basically, a curiosity.
Yes.
Yeah, I wanted to see the world. That was a curiosity. And I kept on traveling around the world. I wanted to learn about what is inside the nucleus and the physics of it. That led me to a different journey, And so I totally agree with you that curiosity is perhaps the most important thing. And with that, I'm going to stop. And if there is any question, anything you would like to ask related to this talk. And there is a silence.
That's all right. It's hard to ask questions always.
Yes.
But you can ask any question. I mean, there is no such thing as a good question. Don't think about it.
That's right. I mean, it's up to you. Otherwise, I'm going to give you a call tonight.
Okay.
I think it's much better that I talk with you on the phone rather than on this Zoom.
Yes, yes.
In about an hour, do you think that's okay?
Yeah, that should be fine. I'm around, no problem.
All right. Thank you so much. I really appreciate it.
Thank you. You're welcome. And I hope the kids enjoyed it.
Yeah. Okay, bye for now.
All right. Bye-bye. Have a good one.